And hello, welcome to the video on solving simultaneous equations, and we're basically assuming that we know how to solve linear simultaneous equations, typically two equations, two unknowns, using elimination and substitution. There are other videos if you don't know how to do those things or you've forgotten to watch, but assuming you've got those, elimination and substitution in particular is going to be modelled, and substitution can sometimes look like when we set two equations equal to each other. That's actually using substitution, and we're extending it out to higher order polynomials, so things such as a combination of, say, a linear function and a quadratic function, and looking at solutions to those. We can have more than one solution. So consider the case where we've got this parabola and the straight line. How many different scenarios can we have? Well, this one here will have two solutions, because you'll remember from your previous work the graphical version of that is when we find the points of intersection. That's the simultaneous solutions. It'll satisfy both functions. But if that blue line was here where it hits it just in one spot, assuming that's a straight line there, that's one spot there, that's a tangent, and that would have one solution. Or if we had, say, this other black line that I'm about to draw here, that won't hit the parabola at all. There's zero solutions, so you can have 0, 1 or 2 solutions with this sort of combination. So it depends on what sort of polynomials are present. We've got an example below where we're going to model this. It's worded, but we can convert it into a graphical situation if we want to, or we can check using our graphics calculators. But looking at the algebraic way of doing this, we want to show that a straight line with this equation meets a parabola with that equation once only. So in other words, it only has one point of contact, probably a little bit like this scenario here. So we're going to show that it's a tangent to the quadratic. Then we're going to use technology on our TI and SPIES to check that out. So what we do is that if we've got y equals 1 minus x, equation 1, and we've got y equals x squared minus 3x plus 2, equation 2, we can substitute 1 into 2. So that's where that substitution method. So wherever we see y, we can replace it with 1 minus x. It's still true. So subbing the result of 1 into 2, instead of writing y, I'm going to write 1 minus x. So 1 minus x equals x squared minus 3x plus 2. So you can see why we sometimes say setting one equation equal to the other. That'll be true at the point or points of intersection. So what we need to do now is solve that, and solving an equation for x is when it's set equal to 0. So we need one of the sides to equal 0. So if we try and aim for the left hand side to be equal to 0, we need to undo the minus x and undo the plus 1. So we're going to subtract 1 and add x, and that will make the side 0. So on this side here, we're going to write down what we had and add x, as I said, and subtract 1. And then we're going to simplify that, and we've got x squared minus 2x plus 1. That's a perfect square. You can factorize that. That'll be x minus 1 all squared. Because remember, a squared minus 2ab plus b squared is the pattern, and that equals 0. So basically that would mean that take the square roots of both sides, and we've got x minus 1 equals 0. Obviously I didn't write plus or minus 0 because that is not a thing. Okay, so 0 is neither positive nor negative. So x equals 1. So we have x equals 1 is the place on the x-axis corresponding to the point of intersection. Now a point of intersection is an ordered pair. Basically it needs an x and a y value to make a coordinate. So we've got 1, and we can use either of these equations here to find the y value. Now let's keep it easy, let's just use equation 1. So y equals 1 minus whatever our value for x is, and it's 1. So 1 minus 1, which is 0. So it's at the point 1, 0. Let's use technology now to check that out. So I've entered those in TI Inspire, and okay, good, that's a good look, isn't it? We've got a linear and a parabola, and we can, depending on what software we're using, if it's Desmos, you just click on the point of intersection. With the TI, you analyze the graph, and we want to find intersection and upper and lower boundaries, and voila, we have 1, 0. Let's compare that to what we had, and oh yes, it was the same. So happy days.